Okay, let's go for the next topic. It's gonna be sources of a magnetic field. The sources of the magnetic field is the electric field, but the electric field when it changes. For example, we know that the intensity of the electric field changes with a distance. Imagine now that we have this point as a reference, point P, and this charge now is in motion with some velocity v, right in the direction to P. Now at this point, the intensity of the electric field changes. Every time the electric field changes, produces a magnetic field. So here in this case we have a magnetic field produced by the change of the electric field at that point. The same thing at any point, correct? We have a change of the electric fields when this charge is moving horizontally. What happens in the other side, like right here, another point? The same thing, right? At this point, because the charge is moving to the right, the intensity of the electric field changes. So we have right here also a magnetic field. So we have magnetic field around right this path because of the motion of these charged particles to the right. So this is the source again of the magnetic field. The change of the electric field at any point, at some point. Correct? Perfect. Now let's try to find a equation that help us to represent the magnetic field right according to these quantities. For example, the magnetic field, this magnetic field right here at this point is proportional to the charge. If we increase the magnitude of the charge, of course, the change right here is gonna be more. So this is proportional. Magnetic field is proportional to the charge. What about if we increase the velocity? If we increase the velocity, at this point, right, the change also increases. So it means that the magnetic field is proportional to the velocity at this point. The velocity of the charge, of course. Now, we found before that when we have a charge, right, going inside of this magnetic field, external magnetic field, correct, we have a force acting on this charge, and that force is proportional to the angle. So we can relate this quantity right here too. So this magnetic field is proportional to sine theta. Remember, we are finding this magnetic field because of the interaction. The interaction are the forces, right? Like in this case, the force between this magnetic field and this magnetic field, correct? And it's found by the experiment that is proportional to sine of the angle between the velocity and this magnetic field. Okay, now let's combine these three factors, and what do we have? The magnetic field is proportional to the charge V sine theta. Now, what happens right here? Well, remember we have electric field, and this electric field changes at this point, and a magnetic field is created. So they are related also. See, we can say that in this case, the electric field is proportional to the inverse square of the distance. The same thing we can say right on the magnetic field. So the magnetic field is going to be also inversely proportional to the distance squared. Now let's write this property right here too, is proportional to the inverse of distance squared. So we can then relate these four quantities to the magnetic field. Perfect. Now let's eliminate this symbol using a constant, the constant of proportionality. So the constant of proportionality is going to be mu naught over 4 pi. This is called the permeability constant, okay? Times what? Times the charge, times V, times sine theta divided by R squared. Correct? Where mu naught is equals to 4 times 4 pi times 10 to the 37 Tesla's meters per ampere. Correct? So we have this equation, right, that gives us the magnetic field created by a moving charge particle. Okay, it's equals to mu naught over 4 pi times the charge times v times sine theta. Perfect. Now, we can represent this quantity using the cross product to make it more compact, right? Because we have sine and we have v. Remember how we define cross product? The cross product is equals to what? Let's say v cos b margin is equals to what? Is equals to a v sine theta. Correct? So we have a vector and sine theta, correct? Like in this case, a vector and sine theta, we can create this notation, the cross product. Okay, perfect. And then we can represent this quantity in this way. A magnetic field is equals to mu naught over 4 pi times the charge times this product, cross product. It's gonna be v cos r hat. Right. In this case, we can represent the vector r, right, equals to the magnitude times the direction, right? In this case, we can say that this unit vector is equals to this vector divided by r. I forgot something right here. It's gonna be r squared, right? R squared. Correct? This is this equation right here. Perfect. And then also we can represent this equation in this way. B equals to mu naught over 4 pi times the charge and the cross product V r, in this case r as a vector, right, divided by r cubed. Perfect. Now this is a case where we have a charge. What about when we have a wire, a conductor? Let's try to find the formula that represents the magnetic field created by the conductor. Correct? Okay, let's do it. Imagine that we have a wire, correct? A wire. Then it has current in that direction. Correct? Current. Let's take a segment, an element of charge right here. It's gonna be the Q, it's gonna be the L, right? The total length is L, correct? You might be looking for a point P, and we are finding the magnetic field at this point, the magnetic field at this point. Okay, perfect. Let's do it. Remember, when we're dealing with conductors, we represent this velocity. This one we have one charge, right? What happens when we have a bunch of charges? Well, the velocity is represented by the v, right? The drift velocity. And drift velocity is gonna be equals to the L over dt. Okay, now let's go back and use the original equation. We use this one. We have B equals to mu naught over 4 pi times, in this case, gonna be this is more charge, this one right here, correct? Now this velocity is gonna be the drift velocity right here, which is dl over dt, correct, times sine theta over r squared. What is this quantity? This quantity is the current. Actually, look, this is the electric field at this point. It's gonna be this small change in the magnetic field. Okay, perfect. So this is equals to the charge, and then we have that this change in V is equals to mu naught over 4 pi times the current, the L, right, sine theta over r squared. The same thing as before, right? We go from this equation using sine to the cross product. We can do it. So let's make the integral of these two sides. So we have that the magnetic field is equals to mu naught over 4 pi times the charge times the cross product of this element of length cross the unit vector, right, r hat divided by r squared. Correct? And we have another formula. It's equals to mu naught. This is a case where we have wires. conductors, where because we're dealing with the current times the integral of the L cross R hat over R squared. This has a special name. This is called the Biot-Savart law. Okay, perfect. Now let's go for the next topic. The next topic is gonna be finding this magnetic field using this equation. Okay, let's do it. We know that if we have a current through this conductor, and if we increase the current, of course we increase the magnetic field. We remember the right-hand rule. If this is the current, the magnetic field, right, is represented by these fingers when they are bent, right? And again, we have the magnetic field, correct, produced by that current in this way, right? Going, let's say, in this direction. Okay, perfect. Imagine that we're looking for the magnitude of this magnetic field at this point P, right? At some distance R from the wire. Okay, great. One more time, if we increase the current, we increase the magnitude or the strength of the magnetic field at this point. So we represent that in this way. The magnetic field is proportional to the current. Okay, now what happens if the current is constant and we change the distance, R? Well, in this case, if the distance R increases, the intensity of the magnetic field decreases. So we represent that quantity, that concept in this way. The magnetic field is inversely proportional to the distance R. These are factors, so we have to multiply these factors to create the general concept of the magnetic field is proportional to the current divided by the distance R. One more time, we need to eliminate this symbol using a constant. Okay, and the new constant, and the constant is going to be the same thing as before. So we have B, the magnetic field is equals to mu naught over 2 pi times current divided by R. Okay, so we have this equation, mu naught over 2 pi current divided by R. This is for long wire, right? For a long wire. Now, let's create this equation using this formula. Let's see if these two are related. Okay, let's do it, or the same. Let's do it. To do this, let's use this wire in this direction. Right? Imagine that at this point, at the center, we're looking for the magnetic field. Again, let's take an element of charge, right? dq. Imagine that the distance from here to here is gonna be y. This is in the y direction. This is in the x direction. Also, we have an element right of this length, which is dl. Our dl was gonna be equals to dy because we are in the y direction. Got it? Now we have a line from that point to from this particle, charged particle, to this point P. Let's call this R, and this distance is called x. From this, from the figure, we can see that R is equals to square root of x squared plus y squared. Also, look, we have right here this unit vector R, and we have right here it's gonna be the L. So this is the angle, right? The angle theta. Correct? But let's find this angle. We know from trigonometry that sine, in this case sine theta, is equals to sine pi minus theta. Correct? And right here sine pi minus theta, according to this figure, is equals to opposite over, right, hypotenuse, x over r. Correct? Perfect. Now let's go back and use this equation. Correct? So that we have B, the magnetic field at that point, is equals to mu naught over 4 pi times the current times the integral. Let's use this cross product, right? It's gonna be this element of length times this unit vector is equals to the L, right, sine theta. But what is sine theta? Sine theta is gonna be x over r, correct? So it's gonna be then x the L over must be divided by r. Also right here we have another r, so it's gonna be x squared plus y squared to the 3/2. Imagine that the limits are from negative a to a, right? But we found that the L is just dy, right, in the direction of dy, so we can change this to dy, correct? Now, by using tables, we have that the magnetic field B is gonna be equals to 4 pi. No, not 4. It's gonna be mu naught. The same thing right here. Current over 4 pi times 2a over x times the square root of x squared plus a squared. This is from tables. Okay, so we have this equation that is found, correct? Now, what happens if this is a long wire? Means that because when I compare to this case, it's for long wire. Okay, means that A must be much larger than R, than X, right? Than X, right here. What happens? Well, this quantity becomes very small, goes to 0, correct? And then this is equals to mu naught current divided by 4 pi is gonna be times 2a, correct? This approaches to 0, this becomes a, x times a, correct? And at the end, what do we have? At the end, we have that B, let me do, well, it's gonna be the same as the, let me do right here. It's gonna be magnetic field is equals to mu naught current divided by 2 pi, correct? This cancels with this, gonna be divided by x. So in this case, x takes the value. Remember when we found this formula, we used this to be r, the distance r. So we take the same notation, right? Instead of x, we take this r. Well, we have the same equation. Okay, perfect. It works. It works. Again, it's gonna be pi minus theta. Okay, pi minus theta. That angle. Great, great. Now let's see what happens when we have a circular path. This is a straight path, let's say a circular path. Let's see what happens. Let's do it. Let's do it. For circular path, let's use again the same formula, right? The Biot-Savart law. And what do we have? One more time, imagine that this is a circular path, correct? We take this segment of this circle, this segment, okay, to the center, and let's find the magnetic field produced by this segment. Okay, let's do it. So we have let's take an element again, dq, but also this represent this element of the length, right? Perfect. Okay, now let's use the equation one more time. B magnetic field is equals to mu naught over 4 pi times the current. Okay, we have the current marching in that direction. Correct. Perfect. And then let's do the integral. Now let's look for these quantities one more time. So according to the figure, what do we have? Well, look, these two are perpendicular. This is the unit vector right here, right? R hat is perpendicular to elements of the length. And this is gonna be then this cross product is equals just to right dl. Perfect. Now let's continue. So let's go back to this equation. What do we have? Gonna be dl over r squared. But what is dl? Well, dl, remember, is we're dealing with this arc length. Remember, we have this formula S as the arc length equals to r times theta. In this case, r is gonna be this r, right? Big r squared. Okay, now from here we have that dl is equals to r d theta. And then what do we have? This equals to mu naught over 4 pi times the current times the integral of r d theta over r squared. Now the angle goes from 0 to theta, right? We can call this theta prime, just to differentiate from this quantity from the integral. Okay, great. And then what do we have at the end for this arc or circular path? We have that b is equals to mu naught over what? 4 pi, right? Times the current, correct? Times the current times the angle theta in radians divided by r, right? This r is cancelled with this. So we have, this is current, right, theta divided by r, right? So this is gonna be for circular path, right? Circular, right, path. Okay, a segment. Great. Perfect. Now let's go to the case when we have two wires, right? When we have two wires and we're looking for the intensity, right, of the magnetic field produced by these two wires at any point. Okay. The intensity of the magnetic field at any point. Okay, great. Imagine that we have these two wires. Okay, these two wires at some distance r, imagine, or d, correct? Distance, okay, distance d, one distance d, okay, perfect. And this is current 1 and this is current 2. Of course we have, right, the magnetic field creation because of the current through these two wires. Okay, let's see, remember when we have a magnetic field, right, and we have a wire inside of this external magnetic field and we have a current, we found that when we use the right hand rule, right, there's a force acting right on this wire, and that force is equals to we found it last time, that force is equals to the current times b, right, sine theta. Okay, so and in this case this is the magnitude. What's the direction? Well, we use the right hand rule, correct? This is the direction of the current, this is the direction of the magnetic field inside, right? The force is gonna be in this direction, right? The force is perpendicular to the plane formed by the velocity and the magnetic field, right? In this way, like in this case. So we have a force acting in this direction. And in this case, if this is the external magnetic field, this is current, let's say current 2. So right here is gonna be current 2 times magnetic field, the magnetic field produced in this case by current 1, right? Current 1, correct? Times times what? Times, what is this V? What is this V right here? We don't need this V, correct? We don't need that V, we need L. Sorry, we need L right here. We need L, the length. Okay, the length L. So in this case, L is the length for each wire. Okay, perfect. This simply happens in this problem. Okay, if the current goes in this direction, so the magnetic field, right, done by produced by this charge, by this current, is gonna be into the wall in this direction and coming out, right, out of the wall in the other side. Correct. This is the magnetic field. Magnetic field, correct. This is the magnetic field. Okay, now this picture is same as this one. So what is the force? What should be the force? So force is equals to what? It's equals to current 2 in this case, current 2 times B1, right? This is the external field. In this case, this field is produced by this charge or this current, correct? Times L times sine theta. Well, what is the angle in this picture? Well, the angle is 90 degrees, so sine theta is gonna be 1. Great. And what is B1? So B1 again is coming from this equation, right, for long wire. Okay, let's do it. So B1 is equals then to, what is B1? B1, where am I? B1 is this one, right? It's gonna be what? Mu naught over 2 pi, correct? Times current, which current is this one? It's gonna be current 1, correct? Times L divided by what? Divided by the distance. We call it D, we call it R, right? Okay, distance, the distance between the two wires. Also, it's better to represent this equation in this way. The force per unit length, right? Force per unit length is equals to mu naught over 2 pi times current 1, current 2 divided by D. In this case, is the distance between these two points, because we're looking for the force, right? The force done on each wire or conductor, right? It's coming in this way. Perfect. So that force is equals to this quantity then, force per unit length, mu naught divided by 2 pi, current 1, current 2 divided by the distance. Now imagine that we're looking for the magnetic field, let's say right here at this point. How we can find that magnetic field? Well, it's gonna be the sum of the magnetic field produced by these two, right, conductors. Perfect. For example, in this case, if this is the distance from the we use R, right? R, the distance R, right? R1 from this point to current or wire 1, and this distance from here to here, right, R2. What should be the magnetic field at this point? The total magnetic field total is equals to, it's a vector, right? Magnetic field produced by current 1 plus magnetic field produced by current 2. All right, this is a very important equation. 2, the total is equals to, right, the sum of these two. We have more wires, we have to add more terms right here. Correct? Perfect. And that's the way how we solve problems. Like in this case, for example, what should be then in this case the total magnetic field is gonna be equals to, what is B1? Well, B1 is gonna be mu naught, right, over 2 pi, correct, times the current over R1. Look, in this case, for both, they are in the same direction, right, coming out. This current produces a field right here, right out of the page. The same thing happens right here, out of the page. So they add, right, they add at that point. So we add again these terms right here. 2 pi R2. What happens if one goes in the opposite direction? Well, like in this case, right? Like in this case. Imagine. Well, in that case, this field is going to be opposite, correct? And we have to establish in this case the direction. If we take this direction to be positive, in the other direction into to be negative, correct? Because in this case the magnetic field produced by this charge 2 goes into the page, right? We just change the signs right here. We have to establish the convention also. Alright, if coming out is positive, it go into it's gonna be negative, well, we can use this notation. Or we want the other way, right? We can use this one negative and this one positive. Depends on the convention. Okay, perfect. Great. Now, let's go for the last topic of this session, right, for chapter 28. The last topic is gonna be the magnetic field in circular loops, produced by circular loops. Let's do it. Let's do it. Magnetic field produced by circular loops, right? Our current circular current loop, right? Using circular, right, current loops. Okay. Remember when we have a circular path like this one loop, we found that at each point we have the creation, we have charge, right? Charge going around this loop, we have the creation of the magnetic field, right? Concentric circles. Alright, this is the magnetic field. Now we can make this in this way. Let's rotate this loop, and now we looks like this. Correct, the same thing. Let's pay attention only on this point, right? What do we have? Well, this is the magnetic field right there, right? This is the magnetic field right here. Correct, like that. Now let's take this picture. Let's rotate even more, and what do we have? Well, imagine that we have this is the loop presented by this segment, correct? This is the front. Imagine that this is the center. Let's start with this element right here, this element right here, for those points, and let's find the magnetic field. Right? The magnetic field is gonna be in this way, right? In this way, in this way. This becomes flat, more and more flat, right? More and more flat, right here at the center. Imagine. The same thing happens right here, right? We have this is the magnetic field right here. Magnetic field, right? The magnetic field, imagine. Correct? Flat and more flat, right? Like this. Okay. Imagine that we have the last one right here. This point and that point right there. Right? Let's do it better. Let me see how we can do better this with this picture right here. Right, like that. This is the X direction, correct? Imagine mine is coming in this way. Right, and this one is coming, imagine, in that way. Okay, remember the magnetic field is perpendicular to the line of force, right here, like in this case, correct? It's gonna be tangent, it's gonna be tangent, right? Tangent to this line, right? Tangent. The same thing happens right here, right? This is the magnetic field is tangent. The same thing for the other one, right? It's gonna be tangent. Correct? Now we can break these are vectors, remember these are vectors, we can break this into components, one in the x direction, this is x, and let's take this is to be y. So one in the x direction, right, which is this, and one in the y direction, right? X direction and y direction. As you can see in the y direction, right, this field is cancelled out. They're opposite at a point. Correct? Only in the x direction we have a net magnetic field. This is this concept to find the magnetic field using circular current loops. Okay, let's do it. Let's do it. So in this case, imagine that we have this loop. We have this loop right here, like this. This is in the x direction. Imagine this is in the y direction. Okay, let's take a point right here. Correct. Let's take an element, dq, right here. Correct. Also, we can make it right in we are taking its image because this is a conductor, right? Image is a conductor. Okay, like that. Okay, great. Now let's take an element, the key right here. Also, we have this the L, right? element of length. Now let's go to this point where we're looking for the magnetic field. And we found that this is the direction is going to be tangent. Imagine this is the curve, correct? So we have the magnetic field in that way. So we have the direction of this element, right, of the magnetic field in that direction. Correct. Also by geometry, right? These are perpendicular, so this is gonna be angle theta, and this is gonna be angle theta, right here. Imagine also that this is r, this time is r, one more time this is x, and this is a, the radius. Correct? We have the unit vector in this direction, r hat, and it's found that the same thing as before. These are perpendicular. The L, right, is perpendicular to r hat. We can see it right away, right? It's the same. Imagine now we're looking in this way, right? So this is the unit vector, right? It's gonna be perpendicular. You can go around you want to, perpendicular to this delta or the L, right? Perfect. Great. Now let's apply then the Biot-Savart law, and what do we have? One more time, right here we have r is equal to square root of what? X squared plus a squared. Okay, perfect. And we're looking for, remember, the component. We have this component in the y direction, and we have this component in the x direction. Correct? In this case, you're looking for the component in the x direction. Correct? Is equals to what? Gonna be this element or quantity of the magnetic field times cosine theta. But cosine theta is equals to what? Cosine theta is equals to a over r, where r again is x squared plus a squared square root. Correct? Perfect. Now let's go again and do the integral right here, applying the Biot-Savart law. And what do we have? This magnetic field in the direction, right? We'll make in this case the integral is equals to what? Mu naught over 4 pi times the current, correct, times the integral of this cross product. Correct? Cross r hat divided by r squared. Times what? Times cosine, right? Times cosine theta. Correct? Okay, and because it's two are perpendicular, right, the sine is gonna be, sine 90 is gonna be 1. Okay, great. So what do we have at the end? Well, we have this equals to mu naught current over 4 pi times what? The cosine theta is gonna be a over r. So it's gonna be the integral of the L over what? X squared plus a squared, correct? To the 3/2. I'm missing something, missing a, right? Missing a right here, right? A goes right there. Okay, now let's do the integral. In this case, the L goes from 0 to 2 pi r, right? Is the circumference, right? Is the length of the total circumference. From 0 to 2 pi a. In this case, r is the radius, but in this case, the radius is a. Great. Now let's do it. Let's do it. Let's do it. So this the magnetic field in the x direction is equals to mu naught, right? Mu naught over 4 pi times the current, correct? Times the current right here. Times what? Times a. It's gonna be okay. A over x squared plus a squared to the 3/2, right? Times, when we integrate dr is gonna be L, and L is equals to 2 pi a. Correct? Finally, we have that this, the magnetic field in the direction is equals to, okay, mu naught current is gonna be a squared divided by 2 times x squared plus a squared to the 3/2. Correct? And that's gonna be the magnetic field along this x-axis, right? Parallel, let's say, to the center of this loop. What happens if we're looking for the magnetic field exactly right here at the center of this circular path of the loop? Okay, let's do it. In that case, x is equals to 0, right? When x equals to 0, what do we have? In this case, we have that b, right, in this, be at the center, and it's gonna be not in the x, it's gonna be an axis, right? The image is the axis right here. Is equals to what? Is equals to mu naught times the current, correct? Times the current. Okay. What else? Divided by 2, and then this becomes what? A 0, and then it's equals to divided by 2a. Correct? Divided by 2a, and this is the equation. What is the formula for the magnetic field at the center at this point? Now, in general, imagine that we have more than one loop. We have n loops. When we have n loops, we have that the magnetic field at the center is equals to mu naught times n times the current divided by 2a, where a is the radius of this circular loop. Okay, perfect. Well, and with this, we finish this analysis. This is half of chapter 28. And let's continue in the second half, right, for this chapter. Okay, thank you, and see you in the next video. Bye.